Okay, so this presentation of the session is structured into 4 parts. First is the Qiskit optimization module. I'd like to introduce this. I'd like to give you an overview about what's in there. Second, I'd like to introduce the optimization via the Ising Hamiltonian formalism. So this is one class of, or covering one class of optimization algorithms that we are looking into. Then I'd like to introduce optimization via Grover search, which we use to solve the same kind of problems, but which uses a completely different technique and will lead to completely different circuits, as you will see. And last, I show a little bit what you can do after that, what you can do with this, further material to get into, and so on. All right. So the Qiskit optimization module. What you see here is an overview of this module, and you see it really covers the high-level modeling down to the quantum hardware. And I'd like to walk you through different parts here. First, the modeling of optimization problems can be done here using DO-Cplex. And DO-Cplex is a high-level modeling language. So this is really convenient to formulate optimization problems. And you can write them down more or less like you would write down the mathematical formulas. And I'll show an example about this in a moment. If you have this, you can convert this to a quadratic program. And this is Qiskit's native representation of optimization problems, so the native representation within the optimization module. And then we have different algorithms, and all optimization algorithms implement the same interface. And you see here is an example. So the optimization algorithm has a method solve, which takes a quadratic program and gives you a result. And independent what kind of technique you use, they all implement this interface, which allows you to very easily compare different algorithms and benchmark them, for example. We have different classes of algorithms. We have classes for QAOAs. This is a class of optimization problems that I get to in a moment. Here's the Grover optimizer, which is leveraging Grover search. We have the minimum eigen optimizer, which is actually an optimizer leveraging this Ising Hamiltonian formalism. And this takes a minimum eigensolver underneath, and we'll also get to that. We have a recursive optimizer. This is a meta heuristic that actually wraps this minimum eigen optimizer. So it takes the minimum eigen optimizer as an input and adds one more layer on top. Then we also have mixed integer programming solvers. So the QAOA solvers only take care of binary variables, and the mixed integer programming solvers can also have continuous variables, for example. And here we have ADMM, that stands for alternating direction method of multipliers. And this is a decomposition scheme. So what this does is it takes a quadratic program and decomposes it in a QAOA, and or in a sequence of QAOAs. And for QAOAs, we can pick one of those solvers, and continuous convex solvers. And continuous convex problems can be solved efficiently classically. So in a way, what this heuristic does is it splits a problem into the hard part, which we try to solve with a quantum algorithm, and an easier part, which we try to solve classically. And then we have some classical solvers like Cplex, which can actually handle some QAOAs and mixed integer programs, and Cobila and SLSQP, which can handle continuous problems, for example, as subroutines here in ADMM. And the quantum algorithms sit on top of Qiskit circuit library, and they leverage the functionality that we have here, as we will see in a bit. And then you can use Qiskit to call or to run these circuits on the real quantum hardware. A more detailed description of the optimization module can be found, for example, here on Medium, on the Medium Qiskit channel. And if you look for this walkthrough of Qiskit's new optimization module, you find the details. Okay, I see one question. How QAOA is classified in that scheme? It's a minimum eigen optimizer, and I will come back to QAOA in particular. All right. So let's move on. This is the overall summary. Now the circuits that we will look into correspond to the minimum eigen optimizer actually, and to QAOA, as we will see, and to Grover search, as I've mentioned before. The other algorithms take these classes as inputs, and therefore they do not lead to any additional circuits, but we use the circuits in a different way. So that's why in this session I focus on these two on these two classes of algorithms. But first, let's talk a little bit more about the problems we'll look into. And I mentioned already a quadratic program. More precisely, it should be called a quadratically constrained quadratic program, but for simplicity, we just drop the first part. So what we want to do is we want to minimize a quadratic objective function as given here over a set of variables x. And we have here a matrix A, the quadratic part, a linear part with a vector b, and a constant offset. And we also have a set of quadratic constraints. Again, we have here a matrix AI, a vector bi, and an offset ci. And we want this term to be less than or equal to 0. We can have a couple of such constraints. Just one comment here. This also contains equality constraints, because you could multiply the left-hand side here by -1 and just add a second constraint, and then this is a way to model an equality constraint. In our representation, you can also just directly set an equality constraint. Now here we say it's a set of variables x. This x can consist of continuous variables, of integer variables, and of binary variables. So this is very generic. And then the matrices A, B, and C, or AI, BI, CI, they live in the corresponding spaces. So this is a very generic class of problems that you can model with DO-Cplex and that our quadratic program class can represent. Now, some of the algorithms we will look into are actually not able to represent this full class of quadratic programs or handle this full class, but can handle a subclass, and that's quadratic unconstrained binary optimization, or QAOA. And as you see here, this class is a subset. So instead of having this full set of variables, we only have binary variables, and we don't have any constraints. We only have this quadratic constraint and the offset. Now you may wonder where the linear part went, since we have binary variables, and for binary variables x squared is just equal to x. The linear part can just be added to the diagonal of the matrix, so it's hidden in the matrix A. All right. So throughout this presentation, I will use two problems usually to illustrate this. The first one is max cut, and the second one is a very simple one, as you see. And this is the instance we'll look into. So we have here a graph on 5 nodes, and you see here the edges. And for simplicity, we assume that every edge has the same weight equal to 1. Then the max cut problem is to split this set of nodes into 2 groups, such that the edges, the number of edges going from one group to the other, is maximized. And I'll show the solution to that in a moment. So this is the graph we consider. And now let's see how to model that with DO-Cplex. Here we have the quadratic objective function we're interested in. So we want to maximize, in this case, this set of binary variables. And the objective is given by the sum over all the edges of the edge weights times this term. And now the binary variable xi denotes whether the node I is in the one class or in the other. So if it's 0, it's in the one class. If it's 1, it's in the other class. And if you look at this expression, if xi, so node x, if node I and node j are in the same class, then this term is 0. Because if they are both 0, then it's clearly 0. If they are both 1, then you have 1 plus 1 minus 2, it's again 0. If they are in different classes, so one of them is 0, then this last term is 0, and one of them is 0 and the other is 1, so this term will be 1. So we are counting exactly those edges where the starting node is in the one class and the end node is in the other class. All right, how to model this in DO-Cplex? You create a model. You create a list of binary variables. Here we create n binary variables. And then you really just say sum over this set here. And we have here the weights. We have here exactly this expression from above, xi plus xj minus 2 times xi xj. And we sum over all the edges. And then we tell it to maximize this objective function. Let's run this. And here you see the result. And you have here the 5 binary variables, the objective function that's coming out of that, and there's no constraint. All right, let's make this a little bit more interesting and add a constraint. And let's suppose we are interested in a max cut problem where the one class has a certain size, and we want to be this size to be equal to b. And so we can just say, for example, b equals 2. We add a constraint, and we say that the sum over the x vector should be equal to b. And here you see the same problem. We maximize this objective subject to this constraint where the sum over the x variables is equal to 2. So this is the problem we want to solve. To formulate this, or to cast this into a quadratic program in Qiskit, that's very easy. You import the quadratic program, you initialize it, and you just load it from DOCplex. You pass this model and you get a quadratic program. And to solve it, you import the Cplex optimizer, for example. This is now a classical solver as a reference. And you initialize that, you just say Cplex solve quadratic program, and you get the result. Now you see 3 of the nodes are put into the one class and 2 in the other. And if you look at the optimal value here, at the optimal solution, you see that exactly 2 variables are 1 and 3 are 0. So this satisfies our constraint. And if you look at this graph carefully, you also see that this is the optimal solution, because there are 5 edges which go from the blue glass into the red one. You have here 2, then you have here 3. And this is the optimal solution. And we keep this in mind for later on, because we want to achieve the same solution with the quantum algorithms. All right. Now let's see how we can solve this problem using the Ising Hamiltonian formalism. And for that, this is working for QAOAs. And Qiskit provides some converters from a quadratic program of a certain format to QAOAs. Because remember, we had a constraint, and the U and the QAOA stands for unconstrained. Qiskit provides this set of converters. The first one is an inequality to equality constraint converter. This takes an inequality constraint and adds slack variables to cast into an equality constraint. And depending on the constraint, it adds integer variables or continuous variables. If we have now an equality constraint, then we can map a linear equality constraint to a quadratic penalty term. So we can move a constraint to the objective function and cast the problem to an unconstrained problem in some situations. And then we have an integer to binary variable converter, which takes integer variables and decomposes them into multiple binary variables, which then can also help to cast a more generic quadratic program into a QAOA. And last, we have this quadratic program to QAOA converter, which just wraps the other 3 for convenience. All right. So let's see how this works for our quadratic program. We initialize the linear equality to penalty converter, and we use it to convert the quadratic program. And now this is what you can get out. And you see that the constraint is gone now, and that the objective function is looking a little bit more complex now, because we added this quadratic penalty term. All right. Now let's check again whether this new quadratic program leads to a similar solution. And we see this. It's doing it again. We get a cut with a value of 5. It's not exactly the same solution as before, but it again satisfies the constraint. We have 2 1s, and it achieves the optimal value. So it's another optimal solution. There are multiple optimal cuts for this problem. And this was just to validate that our converter did a reasonable job. All right, so now let's see how we can take a QAOA and map this to an Ising Hamiltonian. So we assume this given QAOA, as written here at the top. Then the first step is we substitute the variables xi by such expressions here, 1 minus zi over 2. And the zi are now spin variables, and they live in plus minus 1. And you see that if you plug here in a minus 1 or a plus 1, you get back to 0, 1. So this is a reasonable substitution. And then if we reformulated the QAOA to the spin variables, we replace the spin variables by sigma z and sigma zi times sigma zj terms. So where sigma z is a Pauli Z matrix, like given here, and the linear parts, but just by single sigma z matrix. And here we don't have a linear part, but since we have here this constant term, so this introduces linear parts in the spin variables if you have an xi times xj. All right, and what we do by this switch from variables to this Pauli matrices is actually already kind of a switch from variables to qubits. So we identify now every variable with a qubit. So we started with this QAOA at the top. We translated it to an Ising Hamiltonian, which now looks like this. So we have a sum of the quadratic terms, which has these tensor products, and we have the linear parts here with the individual zi, sigma zi terms, and then actually finding the ground state of this Hamiltonian is equivalent to solving the QAOA. So we cast the QAOA into a ground state problem for this Hamiltonian. And this is what you see here. Now, one note, since the sigma z terms are all diagonal, the Hamiltonian H will also be diagonal. And therefore, every computational basis state xn is actually an eigenstate of this Hamiltonian. And so we are searching for the smallest, or for the computational basis state that minimizes the eigenvalue. And then this corresponds to the solution of the QAOA. Let's look at what this means for the problem we started with. So here we look at the quadratic program without the constraint. And this quadratic program provides a 2-Ising method, which returns the Hamiltonian and the constant offset. And what you see is now the offset, that's -2, and the Hamiltonian. Here you have the different Pauli strings. You see here it's a sigma z term, and the identities on the other qubits. You have the linear parts, and here you have the quadratic parts with 2 sigma z terms. And what we can do now is we can also cast this to a matrix, because the Pauli notation is just a more compact notation for a matrix. And we can just ask this Hamiltonian to be cast into a matrix. Then if we check the shape of that, we see it's a 32 times 32 dimensional matrix, which makes sense because it's on 5 qubits. So if we have 5 qubits, the Hilbert space is 2 to the 5 dimensional, which is 32. So the corresponding Hamiltonian here is a 32 times 32 dimensional matrix. As I said, the matrix is diagonal, as you can see here, and by construction it has only real values. And what we do here at the bottom is we plot the eigenvalues with respect to the computational basis states. So the basis states are given here in integers and binary representation, and the y-axis gives you the value of the eigenvalue. And you see here that there are 4 values that are optimal. And here, one note, we converted from a maximization problem now to a minimization, because we're looking for the ground state. So we just multiplied the objective function by -1. That's this. You might realize that here the optimal values go to -3, and we saw before that the optimal value is 5. But this comes from the offset that I showed on the previous slide, which is -2. And if we include this here, then we get back to the -5, which is the negative of the optimal value, because we switched from maximization to minimization. Okay. This is now the Ising Hamiltonian that we are interested in, and we want to find the ground state of that, which corresponds to the optimal solution of the QAOA we started with. How can we find this? And one way to do this is the variational quantum eigensolver. And here, instead of minimizing over all quantum states in this Hilbert space psi, we switch to the minimization over a parameterized subset psi theta. And you see here we minimize now over theta, which are classical parameters, and not over the state anymore. And then we can just use a classical optimizer to find a good set of angles. And maybe you have joined the previous session 2 weeks ago by Julien. He introduced the variational quantum eigensolver using the real amplitude circuit. And this is a circuit coming from the Qiskit circuit library, and we can show this. So here you see a set of single qubit rotations, which are parameterized, and those are some of the parameters we'll optimize. Then you have here set of entangling gates, so 2-qubit gates that are entangled with different qubits. Then you have another layer of single-qubit rotations that are parameterized. So in this example, we have 10 parameters that we are searching over. And yeah, we can run this. Let's try this example here. So we import the VQE algorithm from Qiskit. We give it the Hamiltonian we're interested in and the variational form, the circuit that parameterizes the state space. The backend, we want to run it. Here we use a simulator. And then we run the algorithm. We find the optimal value is -3, which is exactly what we had before. So this is good. And if you look at the probabilities over the different states, we see that it finds this one optimal state with 100% probability. So this is fine. This is working well for this small example. But in general, it's not clear how to choose this variational form psi theta for a particular problem. And I'd now like to introduce a very famous algorithm, the QAOA, that has already been mentioned before in a question, and give some derivation why this is a reasonable heuristic and why this might make sense. And for that, we need to start with the adiabatic theorem, and I'd just like to read this quickly to you. So this says that a physical system remains in its instantaneous eigenstate if a given perturbation is acting on it slowly enough and if there is a gap between the eigenvalue and the rest of the Hamiltonian spectrum. So this might sound a bit complicated to start with, but I'd like to show you what this implies and how we leverage this. And this leads us to trotterized annealing in the end, and I'd like to introduce the general idea here first. Let's suppose we have a cost Hamiltonian HC now that encodes the QAOA we are interested in. Then the idea is that we first find a simple Hamiltonian HX, which has an easy to prepare ground state psi 0, which has a non-zero overlap with the ground state of HC, so of our original problem. Let's assume this is given. I get back to that in a second. Then we slowly drive the system away from psi 0, so the ground state of HX, over a time period from 0 to capital T. And then we do this by following the dynamic of this time-dependent Hamiltonian HT, which is given like that. And you see this is a convex combination of HC and HX, and at time t equals 0, it's just equal to HX, and then it slowly moves to HZ. So we start in HX, and then we transition to HC. And if this is done slowly enough, then the adiabatic theorem implies that the system will always stay in the ground state of the Hamiltonian HT. So at time 0, we stay in the ground state of HX, which is psi 0, and then at time capital T, we end up in the ground state of HC, which is solution of our problem. Okay, so how do we choose this HX? And a common choice here is setting HX equal to the sum of sigma x terms on the ith qubit. So given like that. This is nice because it's easy to prepare. It's just these single qubit Paulis. And the ground state of this is actually given by the equal superposition state, which we have here. And this is also equal to easy to prepare just by Hadamard gates. And another thing is that this equal superposition state has actually a non-zero overlap with every possible basis state. So it has a non-zero overlap also with the optimal solution, that is a ground state of HC. So this choice actually satisfies everything that we need. Good. Let's now use a very simple example, a single qubit example. And let's suppose that that HC, a cost Hamiltonian, is actually equal to sigma z. And this is given like that. So the 0 state will have the eigenvalue 1, and the 1 state will have the eigenvalue -1. And that's obviously the ground state, the 1. And the optimal value will be -1. Then the dynamics that we want to apply, HT, are given like this. So HC is sigma z, and here we have minus sigma x. And the annealing process can then be approximated by setting the states like this. So we updating the state psi from psi t to psi t plus 1 by applying e to the minus I ht, which is this Hamiltonian, times a small time step. Now the problem is these matrices sigma z and sigma x, they don't commute. However, what we can do is we can trotterize. That essentially means we choose the sigma t very small and we apply these two gates individually. So we first apply this e to the minus I hc, and then we apply the e to the minus I and so on hx. And for a sufficiently small time step, we only introduce a small error. So if we look at these terms and we rewrite them a little bit, and introducing this angle gamma t, then this is nothing else but a RZ rotation for this angle gamma, which is defined here. And for the hx part, it's just an Rx rotation for the different angle. And so a single step of trotterized annealing is very easy to implement as a quantum circuit. You have a single qubit here. You apply a Hadamard to initialize the equal superposition state, and then you have the RZ and the Rx. But then, of course, we want to do this a couple of times to really simulate this annealing process. And for that, we need to construct this schedule. And here, what we do is we want to simulate for a time t, and we want to discretize with n steps. So the time step in between will be delta t, which is just t over n. And now we construct the sequence of parameters gammas and betas for the cost Hamiltonian and the mixing Hamiltonian part. And this is exactly what you've seen before. So we compute the time at step I, and then we have here delta t times t over capital T for the gamma, and here the same with 1 minus t over capital T for beta. And this factor 2 here is just to compensate that the Pauli rotations divide the angle by a factor of 2. All right, then we simulate for time here up to 5, and we do 10 steps, and we construct the schedule. And here this will look very simple. So we go from 0 up to 1 for the gammas, and from -1 up to 0 for the betas. And let's see what this does in terms of quantum circuit. This is now looking like that, and you see it's just repeating the same pattern where the parameters for RZ, for example, go from 0 up to 1, and from Rx go from -1 up to 0. And what we do here is we track the probabilities at every barrier here to measure a 1 or a 0 of this one qubit. And we can show how this looks like. And here in green, you have the probability of measuring a 1, and in blue, you have the probability of measuring a 0. And you see, we start with the probability 50-50, which is the equal superposition state, which makes sense. And then we move up here to 1 to measure a 1, and the probability of 0 goes down to 0. So this is what the annealing process, the trotterized annealing. If we look at the objective function, which is the expected value of the Hamiltonian, then we see that this is going from 0 down to -1, which is the optimal solution of the problem. Good. This was for a single qubit, a very simple example. Now let's briefly look into how this can go work for multiple qubits. So we have again our cost Hamiltonian here, which has a sigma zi tensor sigma zj term, and here the individual sigma zi terms. Now all of them are diagonal, so all of them commute, and therefore we can write this e to the minus I hc gamma that we need in the trotterization, just like the individual, like a product of the individual terms. So we have here at the end the product over the single qubit terms. So these are just RZ rotations again, and here we have this sigma z times sigma z rotation gate. And for this we need to implement this RZZ gate, and I'll get back to that in a second. For the HX terms, these are again just single qubit RX rotations, because those are the single qubit gates as we've seen earlier. So how does this RZZ gate work? This is a way how to decompose it. So you start on 2 qubits, you apply a controlled NOT gate, a Z rotation, and another controlled NOT gate. But for convenience, this is also implemented directly in Qiskit, but in the end, it's decomposed again to this first version. So we started with trotterized annealing, but in the end, as mentioned at the beginning, we want to look into QAOA. Now, how is this two related? Actually, it's very closely related, because the problem with trotterized annealing is that it leads to very long circuits if the problem size increases, and you have to do because you have to do a large number of steps with increasing problem size. So the idea of QAOA is to just restrict this number of steps to some given number p, and how to choose this and for which problems you might choose this constant and so on. This is actually still not fully understood, and only for some special cases, and is still an open question. So we won't address that here. We will just assume we set this p to a fixed number, and then instead of following a annealing schedule like the one I've showed, we actually let a classical optimizer find these angles beta and gamma. And this, if we apply these changes, so we fix the number of steps to be p, and we optimize over these angles instead of using an annealing schedule, then we end up at QAOA. And this has been introduced here by Edward Fari and co-authors in this paper. Okay, let's again use this very simple example to illustrate that. So first we introduce a classical optimizer. Here we use Cobila. And then we construct the QAOA circuit for depth equals 1. We have this parameter gamma and beta. We introduce a single qubit circuit. We start with a Hadamard, and then we apply a RZ and an RX gate. Then we construct an objective function which takes parameters which are mapped to gamma and beta then. And we, for a given set of parameters, we evaluate, in this case, for simplicity, the probabilities again of measuring a 1 or a 0, and we compute the corresponding objective value. So this is just a compact notation for the expected value of the Hamiltonian for the state that we construct here. And then we use this optimizer, Cobila in this case, to minimize the objective function over the parameters. If we run this, we see that with a single step QAOA, we actually find the optimal value of -1. And the state has all the math, all the probability mass at the 1, which is the optimal solution. So in this very simple example, step 1 QAOA was actually able to find the optimal solution with 100% probability. So this is quite nice, but of course this is in general not representative, as we will see. But this illustrates the idea that instead of having a long annealing schedule, you cut off the depth of the steps, and you optimize over the parameters. Now, in Qiskit, we have this QAOA variational form. And I'm now quickly jumping back to trotterized annealing to show the link again. This variational form is a variational circuit similar to the one that I've shown in previous slides. And we can use this to reconstruct trotterized annealing by just constructing the schedule again as before. Now we choose 10 time steps and 10 and 20 discretization steps, and we use now the Hamiltonian that we constructed for the max cut problem. And we say that the QAOA var form should use n+1 steps, and then we construct a circuit with the parameters that we got from the schedule, and we evaluate the state vector. And we should import this first. Okay, so this gives us the state vector for this variational form, and if we analyze this, so here I'm now plotting the probabilities, then you see that again the 4 optimal states have the highest probability, and then the others get a little bit of probability, but this is because it's still an optimization, an approximation. Otherwise, we would have to choose the t or the n larger. So this is the QAOA variational form used to run trotterized annealing. Now we want to use actually QAOA. Now first we quickly look at the resulting circuit. So this is again for depth 1, just to make it short, because otherwise it's getting a bit long. So we have the 5 qubits from our 5-node max cut problem. We initialize in Hadamards to get the equal superposition state. Then we have here the quadratic parts. This is this RZZ gate that I've shown before. And then we have here a few few single qubit RZ gates. This is for the linear parts, and then at the end we have these Rx rotations for the mixing Hamiltonian. So this is the variational form, and if we do trotterized annealing, you would have to repeat this many times, so 20 times in the example that I've shown. Now let's see how QAOA actually performs for MaxCut. So we initialize QAOA from imported from Qiskit. We give it the Hamiltonian. We set the depth that we want. So we want one step. We give it the classical optimizer, and then we in the backend and we run it. And now you see we do not get -3 anymore. The value we get is -1.8 roughly. You see the optimal parameters that we get out. But for this small problem, we can evaluate the probability of measuring an optimal solution. You see this is around 30%, which is not too bad. And we can look at the full histogram that comes out of this. And you see here the optimal solutions, they clearly stick out. But the other states still get some probability. And this is because we cut off at one step. But still, this is a reasonable result. We find the optimal solution, and we can solve the problem we started with. All right. So this was now derivation of QAOA. So what did we do? We started with a quadratic program that had a constraint. Then we mapped the constraint to the objective function. We mapped the resulting QAOA to an Ising Hamiltonian. We constructed a circuit based on that. We used the classical optimizer to find the best parameters and then read out the optimal solution. And this is all done actually now by the minimum eigen optimizer for us. And how is it used? You import the minimum eigen optimizer, and then you give it the QAOA that we've used before as a minimum eigensolver. So the minimum eigen optimizer is a wrapper for all the techniques that use or that can find ground states of Hamiltonians or approximate ground states of Hamiltonians. And QAOA is one of those. There are also quantum phase estimation based things or VQE in general if you use other circuits. And you can plug all of them into the minimum eigensolver and then just say solve quadratic program. And this gives you the result for that. And look here, this is the quadratic program with the equality constraint that we had before. So this really does everything that we've discussed so far for you, all the translations to the circuits and back. And if you run this, takes a second, and look at the results in a second. So there's one question: how to implement with a larger number of steps. So you can just tell the QAOA minimum eigensolver here how many steps you want to use, and then the minimum eigen optimizer will use QAOA with this number of steps. And if you talk about steps of the classical optimizer, you can also provide that here and specify the classical optimizer with the parameters that you're interested in. All right, so you see the optimal solution. It's the same as before. Its objective value is 5. We get here 1, 0, 1, 0, 0. It's illustrated here, and it's again one of the 4 optimal solutions to this problem. And this kind of summarizes this first part, which is on this minimum eigen optimizer, or all this Hamiltonian, Ising Hamiltonian based optimization techniques. All right. Now, in the third part here, I would like to discuss Grover adaptive search or optimization via Grover adaptive search. To recap, Grover search is the following. So we suppose you have a Boolean function f that takes values in 0 to 2 to the n minus 1, and that maps the value of this set to 0 or 1. And also suppose an oracle OF such that it maps a state xn to plus xn if f is 0 and minus xn if f is 1. Then Grover search allows you to find an x such that f of x is 1 using only order of square root of 2 to the n queries to the oracle. while the best classical approach requires order of 2 to the n queries to the function f. So this is very simplified Grover search, and I don't want to go into more detail here on that. Then what is Grover adaptive search? Grover adaptive search now assumes a function f from the same set to, here for simplicity we say to the integers. And in addition we assume some input x prime out of this set. And then we want to have an oracle OF of x prime that actually maps xn to plus xn if f of x is larger than or equal to f of x prime, and to minus xn if f of x is below f of x prime. And if we have such an oracle, then we can run Grover search to find an x where f of x is less than f of x prime. And if we found such a x, then we just replace x prime by x. And then we repeat this whole process until we can't make any improvement anymore. And this gives us almost a quadratic improvement of finding the minimum of f over brute force search. Okay, so the main question now is, of course, how can we construct such an oracle f of x prime? And we introduced this in a recent paper together with my collaborators here from JP Morgan Chase. And I'd like to explain how these circuits can be constructed, particularly for QAOs. All right, there are two things we need for that. The first is the 2's complement to represent negative integers, and it's illustrated here. On 4 qubits, from 0 to 7, it's as you would expect. You see, it's just counting up in the normal encoding. However, for the negative, the first qubit here, or the most significant qubit, indicates whether the number is positive or negative. And if it's negative, then we do not count as you would expect, but we count in the other direction. And this has some nice properties, like the arithmetic operations are more or less the same now with signed numbers compared to unsigned numbers, and this allows efficient implementation and things like that. And this is something that also very naturally fits into our context, and we'll see this in a bit. So here, just for simplicity, we have a function that does this encoding. So it takes a bit string and the number of bits we have in total, and it returns the integer. So here, if we have 0, 0, 1, 1 on 4 bits, we get a 3. And if we have 1, 0, 1, 1 on 4 bits, then we get a -5. So just to illustrate this. Now, the second thing we need is a phase encoding in the QFT, the quantum Fourier transform. Suppose we have a fixed integer k, and we are starting in the plus state, so in the equal superposition state on n qubits. Then we can easily construct such a state here. And you see this is normalized at the beginning, and then here the amplitudes for the basis states are e to the 2 pi I x k over 2 to the n. And this is equal to easy to prepare with just single qubit RZ gates, where we choose the angles like that, where we have 2 pi, 2 to the I on the ith qubit divided by 2 to the n times k. So we encode the x using here the qubit count, and the k is fixed. And this works because we apply this to the equal superposition state, and we denote this single qubit operations by uk here. If we apply an inverse quantum Fourier transform to this state, then you can check the definitions. Then this gives us nothing else but k in the binary encoding on n qubits. If we now have k1 and k2, two integers, and we apply uk1 and uk2 to this plus state, and then the inverse quantum Fourier transform, then we just get the sum here. And you might have heard about QFT adders for quantum arithmetic. That's exactly the same idea. Good. Now, let's illustrate this. So we import the QFT from the Qiskit circuit library. Then here we have this encode function, which just constructs a circuit that applies the single qubit z rotations with the angle that we discussed a second ago. And what we do here is we first apply the Hadamard to get the plus state. Then we apply this encode function here, in this case on the value 2. Then we apply an inverse quantum Fourier transform, and we measure the qubits. And this is the same circuit. And if we execute this, and here use a simulator, and we look what happens, then we measure exactly 0, 0, 1, 0, which is the 2. Here this is translating the 2's complement, which we were encoding. And if we use some different encodings, here we encode -3, we get that. Or if we encode 4, this is what we see. And it's nice because if we now add 2 of them, we get the sum, as mentioned before. Now we have the 6. If we do the -3, we have the 3 again. And this is now, actually the negative numbers are now in this encoding, because this is now via the rotations, this is natively going to the 2's complement. All right. Let's have a look at a little bit more complex circuit. So what we did here is we have now 3 qubits that we add, 3 input qubits, and we apply the Hadamard gates to them. So we bring them into equal superposition. That's what you see here. And then we apply this encode gate that we have seen before, controlled by these input qubits. So here we use 2 controls, actually the first one and the qubit 0 and the qubit 2 to control the encoding of 2. Then we control the -3 with the qubit 1 here, and the +4 with the qubit 2. And then we apply the inverse quantum Fourier transform and we measure. If we look what comes out here, then these are the counts. You have here in the first column, you have the input of the control qubits. And in the second column, you have the 2's complement representation of the result. And then here you have the integers. And you see if we have 0, 0, 0, then we don't add anything, we get a 0. If we have 0, 0, 1, then we still get a 0 because the first encode had 2 control qubits, and here we only have 1, which is equal to 1. And then if you go through that, like for example the 1, 1, 1, there you see that we add up all of them, we end up with a 3 as before. So now we have a superposition state that has all the possible inputs on X and computes this output with this conditional sums as indicated. Now, what is this circuit actually doing? If we think of the input as a 3-bit, as 3 variables, bit variables, Boolean variables, then this circuit actually computes the function q of x equal to 2x0 x2 minus 3x1 plus 4x2 into the second register. So this provides us a systematic approach to construct arithmetic circuits, and this works for arbitrary polynomials in binary variables. And this is particularly suited for QAOAs, as we are interested in. And actually this QX here is a QAOA. Okay. In Qiskit, we have the quadratic form in the Qiskit circuit library, and this is actually implementing exactly what I just said. And what we take here is from the quadratic program without constraints for maxcut. We take from the objective function the matrix, the vector, and the offset, and we set the number of values, the number of qubits we want to use for the value representation. And then we construct this quadratic form based on these inputs, and this is the result that you see. So we have 5 input qubits and then 5 value qubits. And here this controlled controlled Z rotations, these are the linear terms. These U1 gates at the beginning are the constant offset, and then here at the end you see 2 controlled gates. These are the quadratic parts. And at the very end, you have the inverse quantum Fourier transform. Now, you see this is a rather long circuit, and this gives you an indication that Grover search or Grover adaptive search likely requires a fault-tolerant quantum computer and will probably not be really applicable on interesting size problems or productive problems on a noisy quantum computer. So what we do here is we apply Hadamard to the input register. We apply this quadratic form and we measure just to show what the result is. And we again run this on the simulator. Now in the first column you're going to have all the inputs. Then you have the binary representation of the output and the integer representation. And for reference, we evaluated here the objective function of the quadratic program again. And you see that this matches nicely. And if you scroll a bit down, you see that here are 4 solutions that achieve the optimal value 5, and those are exactly the ones that we've seen before, which have 2 1s and lead to 5, a max cut of 5. Okay, so how does this link to Grover adaptive search? Now we have a single qubit that actually indicates whether a value is negative or not from the 2's complement. And from the construction, we can easily add an offset that shifts our objective function up or down. So what we can do is we can apply Grover search to find a negative value. And if we found a negative value, we shift our objective function up such that this value becomes 0. And then we look for the new negative values and for the remaining negative values, which are all those that are better than what we've seen before. And so if we run this, this is now actually the oracle. So we apply the quadratic form. We apply a single C gate on the sign qubit, because that flips, if the sign qubit is 1, this flips the phase, and otherwise it does nothing. And then we uncompute the quadratic form. And this is the oracle for Grover adaptive search. So this is the OF of X prime, essentially. And now let's look into how this is done in Qiskit optimization. So we import the Grover optimizer. We initialize this, we tell it how many value qubits, we give it a backend. Here I set the penalty term of the converter to 1. This is to save value qubits, otherwise I would have to give a bit more value qubits, but 1 is sufficient for this problem. And then we actually run it. So this takes a few seconds, because this is now actually a 10-qubit simulation, or a couple of 10-qubit simulations, because we have 5 input qubits and 5 value qubits, and then we run this quadratic form on top of that. So let's recap again what this method actually does. This takes a quadratic program which had a constraint. It maps this to a quadratic program without a constraint and only binary variables, so a QAOA. It translates this QAOA into these oracles for Grover search, and then it adaptively changes these oracles and runs Grover search again and again to find better and better values. And after a while, this comes back and gives us also the optimal result. But it looks like screen sharing takes quite a significant part of my CPU power, so this takes a bit longer. So I mentioned this already. The first part, the QAOA and so on, these are algorithms which have this variational character, where you have a classical optimizer that runs over the parameters. And for those, we hope that they can be applied to noisy quantum computers, and that that they help speeding up some optimization tasks. But those are heuristics, so we don't have any guarantee. For this Grover-based optimization, you've seen that the circuits get way longer, but here we have actually a theory that tells us that we can get a quadratic speedup over brute force search for combinatorial optimization. So this is kind of nice, but this likely requires a fault-tolerant quantum computer. But you see that in Qiskit optimization, you can very easily test 2 completely different algorithms on the same problem, and the only thing you have to change is actually which algorithm you import. On top of that, the minimum eigen optimizer, you have seen this is built in a very modular way. So you can replace the minimum eigensolver that you use, and you can plug the minimum eigen optimizer and a recursive minimum eigen optimizer and so on. And this modular way is really to boost research, so that you can replace whatever part of the algorithm you want and test your own components to to see how they work, how they compare, to benchmark. And here you can also use the, as I showed, the classical solvers like Cplex to benchmark. And this benchmarking is not so interesting on 5 problems. Here it's more for validation to see that we found the optimal solution. But if these problems grow a bit larger, then at some point it will be really interesting to compare how well does Cplex, for example, which is a commercial solver, compare to how to QAOA or the other things that we can run. You see here, this leads to an optimal solution. We get the value of 5, and it's, I think we have seen this before, the 10001, and the solution is illustrated here. All right, so what's next? There are a few resources that I can recommend to dive deeper into these topics. The first is the Medium article that I mentioned that discusses the Qiskit optimization module in more detail, and you can find it under medium.com/Qiskit. And the second is the Qiskit textbook, and this has sections on QAOA and Grover search, and also on the things that are used within. So this is a good resource to get started. And we have Qiskit tutorials on multiple topics, but also on optimization. So in the Qiskit tutorials, you find tutorials that introduce the quadratic program, how to use this, that introduce the converters, how to map quadratic programs to QAOAs if possible, that show how the minimum eigen optimizer works, how the recursive minimum eigen optimizer works, how Grover optimizer works, and also how ADMM works. So this provides the tutorials to the full functionality of Qiskit's optimization module. Now, if you what can you do next if you want to do something hands-on? Of course, modeling optimization problems is with DO-Cplex very, very easy. And DO-Cplex is for free if you install the community version, which runs to, I don't know, probably a few hundred variables. For testing these algorithms, this should be fine. But also the quadratic program in Qiskit can be used directly to model your problems. And so one thing you can easily try is model your own problems of interest and test the different optimizers that we provide in Qiskit's optimization module and get familiar with them. Particularly the ones that I have not shown in this tutorial, the recursive minimum eigen optimizer, for example, and the ADMM. And in the tutorials, but also in the Medium article, you find the references to all of these, like also the papers on where these have been introduced. And last, of course, Qiskit is open source, so you're very welcome to contribute and include your own quantum optimization algorithms if you have some that you would like to include. Feel free to reach out to us, and we're happy to discuss with you on that and to help you integrate that. And with this, I'm at the end of this presentation, and I'm very happy to take any further questions if there are. Maybe one more question. I think we are also right at the top of the hour. So what's the size of the optimization problem that we can solve with QAOA on the machines with the highest quantum volume or highest number of qubits? So that depends very much on the problem you're looking at, because one problem that we have when mapping the QAOA circuits to the hardware is that if you have a dense problem, that means you have quadratic terms between all variables. You also need dense connectivity to map this. So you have a lot of swap gates, and this gets getting too long. If you have a sparse problem with ideally even one where the 2-qubit terms, the quadratic terms, match the hardware connectivity, then you can do way more because you don't have to do any swaps. So right now, I would say that it's probably around 10-ish, depending on the problem. And with that, I thank you again for your attention and for joining this session. And I wish you all a very nice day or evening, and hope to see you in the Qiskit Slack workspace, for example, and contributing your research or your algorithms. Thanks and goodbye.